Last day, got all your tests and everything else that you've never collected going there. How do you know I have the right grade? You're not picking this stuff up. Who am I kidding? You're not here, right? So anyway, so I'm going to return everything. I just realized I didn't even figure out what the average of the test was because it was so freaking high. It was really good. I'm not sure what the average is, so I wouldn't be surprised if it was 90. I've never had this happen. The third test is always the worst. And I did not dumb this test down by any means. It's just the same as any other third test I've ever done. You know, I just take the old test and I write new questions where the old ones were. Generally kind of similar, but not the same, so that I have new tests. So anyway, I also checked my test in case you're wondering against Florida State, Caltech, MIT, Urbana. You know, other people post their tests online. Mine really are no different. Except they tend to be more shorter questions. That's just kind of my little flavor on things. So again, you did very, very well. You heard from me if you didn't. And if you want to know all your grades, make sure I got it right. Just email me. I don't have any other better way to do that. And homework. So in terms of what will be on the test, I will have. I've started on the final. I've written half of it. I can tell you, I do have a symmetry question. All right, so we do have to calm down 1 hour. All right. And it does emphasize the first and second tests a lot more than the third, even though I don't know if that's necessarily a good thing. It did so well. Friday, I will tell you, I'll give you percentages. I'll tell you, 5 questions on this, 6 questions on that. I'll give you a good idea. Now, also, Friday is a really tough day for me. I'm going to talk straight. Maybe 1 5-minute break to charge up the camera. See that it's okay now, whatever. I think I'll bring a second battery. So depending on how fast I think I can do this, I may just talk 2 hours straight. It's pretty rough. So anyway, go easy on the 9-time loser of the Sergeant Silver Circle Award. Just found out this morning, another nomination, another award. Thank you. Awesome. Anyway, so that sucks. They actually stopped telling. See, they used to tell faculty they were nominated for the Silver Circle, but they stopped because I kept losing over and over again. So now you just find out if you won the day of. So anyway, boo-hoo for me.
I voted for you.
Thank you. At least I'm still. I got Monday. I got Monday. And at home I got kitties. Cat food. Anyway, my kitties call questions. What's that?
You get cat food if you ask a question.
Catherine is right? Having money problems, like if you want to save money, folks, don't go with cat food, go with dog food. Just so you know, all right. Cat food's actually pretty expensive, so. Look, this is $1.10 from Kmart. Fancy feast. It does smell really good. I probably will taste it at some point. But seriously, $1 for this, that's actually pretty expensive. So, as for these potatoes, I don't know why, I just have potatoes. Want the potato? All right, everyone, come on now, we got to get through this. I actually have a bit of a rough lecture. This is kind of long, I'm going to barely get done on time, and I have to give you your test back, all right? Please take your stuff. I don't want to keep it myself, right? It just takes up room. Okay, so getting on the actual lecture, wasted enough time. And I did email you, remember, the exam is actually on a Monday at 8. That sucks. Sorry, I got that wrong on the calendar. Calendar's been fixed. It is in here. It's just 2 hours. It's not going to be like twice, all right? And so other of you folks, just meet me here, and then we'll go upstairs, if that's whatever. So we'll have that in here, and I expect to give you all this is going to be the highest scoring class in history, so that's very good. Don't let it get to your head, all right? And I don't think unless you have any questions for me, I'm pretty much done. You got a question?
You gave us like 2 hours for like a standard exam, so is the final exam still going to be about the same length?
Yeah, it's exactly. All the tests have been pretty much identical, with the first one being a little longer because of that units section, but I just simply been removed. Other than that, it's identical. Yeah. I'll tell you, all right, so if you have a couple other questions, I'll tell you more Friday. For derivations, I'm definitely going to do a dx with changing y at constant z question. I'm definitely going to do that. And I'm leaning towards let me tell you Friday, but I'm leaning towards a Van der Waals type of question. Maybe both, right? You know I can combine those. So other than that, I don't have much, and I'd rather write the whole test and talk about it on Friday. So, and there is one of these questions, so just one, right? So that way it's meaningful, you bother to come. And if there's no other questions, we're okay. Okay, now remember what we've gone over so far is symmetry operations, right? That is, can I rotate something? And that was called that like a C2 rotation if I can turn something to 180. And that means that the molecule hasn't changed. And that means that if I perform an operation on a molecule and the molecule doesn't change, then it possesses that type of symmetry. We did rotations, reflections across a plane, just this very obvious stuff. Inversions, that's a little trickier. Improper rotation, now that one was kind of a strange bird, a rotation followed by a reflection. And then there was also the do nothing symmetry element. Okay, then we started looking at molecules and saying, what of all of these operations, how many of them do I have? Can I rotate it 2 ways? Can I rotate it 3 ways? I mean, ammonia 3, water 2. And I collect all of those things, and once I know them all, I can then start assigning its point group. And again, it's just a laundry list. There's actually flow charts that help you look at a molecule and figure out what point group it's in. We also talked about how they have multiplication tables. What happens when you rotate something and then reflect it. So we did a little bit of that last time. So then I got to C2D and we looked at water. Let me continue on, and then I'm going to give you an example at the end of class of where this stuff is actually useful. It's actually a calculation that me and my grad student just did. I'm going to actually repeat that calculation for you. It's going to appear in the paper. So one of the few times research active faculties, I know generally we're the worst teachers as opposed to lecturers who teach full time. If they don't do a good job, they're let go. They can't really do that to me. So it can only make me lose awards. But it is good that I can show you something that me and a grad student actually worked on to produce a scientific result, which we did just a few months ago in a paper being written now. Okay, anyway, all right, more point groups. I'm not going to go over all of them. Let's see, just to give you an idea, let's see, this has a CN axis with the horizontal mirror plane that I screwed up last time. Horizontal mirror plane. Remember that a sigma, because I need to use shorthand, this just hurts. An example of this one is, some of these are kind of hard to draw too. CHH, if I don't draw C, you notice there's a carbon there, carbon, H. Good about this one is that I can cleanly draw this into the board. You know, it's always a crazy problem having to draw three-dimensional things in 2 dimensions. I don't know how they do it in organic, for too long since I had it. Okay, so in the horizontal mirror plane, well, for one, I can see that the rotation, I'm going to grab it like this and spin it, and I can see a C2 rotation, but it has a horizontal mirror plane that is perpendicular to the rotation. Remember, these guys are, they traverse the rotational axis. This one goes across it, and you see where's the plane? It's the board itself, right? Yeah, of course, it's right on the board. And don't forget, it's kind of tricky, you might know it's good. When you reflect through the middle, remember that these atoms have top and bottom parts, and those actually get switched. That actually matters. That came up when we did operations on water at the very end of the last lecture, so you might want to watch that. You're not going to want more. Anyway, okay, so, Dn. Okay, Dn has a Cn axis. A lot of things rotate. And a C2 that is perpendicular. All right, so maybe just write down. I did this last time. And a C2 that's perpendicular to the Cn axis. Okay, so you might want to just write that out in case you get lost in my shorthand. Okay, now as I was looking up examples of these guys, as I looked up examples of these guys, this is like the most horrendously complicated of all the point groups. The examples of molecules with Dn symmetry, I cannot even draw them. I couldn't even look at them on my computer and figure out what the heck I was seeing. So they're always chiral and very complicated and rare. It doesn't sound like it's that complicated, but it is. Okay. Then we got, now here's one that does come up a lot, DMD. Dungeons and Dragons. We got a LARPer in the room? DMD, Cn axis, then I've got N perpendicular C2 axes, and a horizontal mirror plane. Sorry, I'm in the way. A horizontal mirror plane perpendicular to the Cn axis. Wait. No, sorry.
That's a
Yeah.
CNH. So it has to be
I screwed that up, sorry.
diagonal.
Yeah, it's just, sorry. I got it. Okay, Cn axis, sorry, I just looked at the wrong thing in my notes the first time I was teaching this stuff. A perpendicular C2 axis and a dihedral mirror plane. Sorry, that's that. Okay, now I kind of like this one because the example was extremely difficult for me to figure out. Here, I don't want to. Let me do a D2D example. Because this one kind of fascinated me because I had to stare at it for a really long time. So this is a boron molecule. Okay, so these right now are done in the plane, and these are out of the plane. Bigger. Okay, so that one's coming at me, and that one's coming out of the board, that one's going into the board. Okay, so I looked at this, this took me forever. So this one's kind of interesting that it actually does this. I see a C, so D2D, so I have a C2 axis, which is clearly here. I can clearly see that I spin that 180, I get the same molecule. I can see the dihedral mirror plane is actually is in the board or perpendicular to the board. It clearly, the plane that goes through this guy then just bisects that guy, and then of course I can turn that 90 degrees, so I see the mirror planes. But I swear to God, I have to have the perpendicular C2 axes. And I swear to God, I looked at this, I said, what the hell? How can this be D2D? Because if I turn this 180, it's not the same, right? These are not in the plane, and these are. If I turn it 180, that's not true anymore. And I was just dumbfounded. How could this be true? I found a YouTube video. Someone had posted a YouTube video to explain how it is D2D. The answer is that the C2 axis, you see, I'm trying to turn it as it is. I'm trying to pick it up as it is and flip it over. That's not the right axis. The C2 axis is not here. It's actually diagonal. So having a diagonal, so the C2 axes, well, there's two of them. C2. It's not going to just move this way. It's actually going to, I don't even know if I can do this. It's going to flip and rotate them I can't do it. Anyway, it's going to flip them and rotate them at the same time because the axes are not just straight in or up. So I can't really describe that unless you see the video. So anyway, just an example. Let's see, where am I at? D2, let me go to the new board because this one is one of my favorites. Because I study a lot of stuff that has the symmetry. One of the easier ones to see, we've been doing a lot of work with polyaromatics, DNH. Okay, DNH has a C of axis, N perpendicular C2 axes, okay, a horizontal mirror plane, and that is perpendicular the C and axis. Okay, so look, it'd actually be okay if you maybe didn't even write this down, just kind of absorb. I'm not going to do something like, tell me what a DNH point group is. I'm not going to do that on the test, right? That's just kind of stupid. You use flowcharts to really figure these out. I just want to show you all the flavors of this. Now, this guy is important because it's this one. All right, benzene. All right, benzene is D6H. Okay, now, let's see. All right, so the plane is obvious. It's the plane of the board, so I got that guy. Let's see. This is okay. Where's my 6 principal axis? Is technically the highest number on your CN axis. I can see that clearly. That axis is right. It's going this way because I can turn it 1/6 of 2 pi 6 times to get it back to itself. So that one's obvious. And then I have to have 6 C2 axes. So I have to be able to flip it like a pancake. And here's the thing, I see 1, I see 2, I didn't draw it super well, you can kind of tell. I can see 3. Where's the other 3? I'm missing 3.
Through the bottom.
Anybody?
Through the bottom.
Dang, you weren't even answering.
Oh, yeah.
All right, it's fine. It's here. Here they are. Right, you can see how it's obvious that you can turn into 180 that way. So, then we've got one I will show an example of, an SN. It's just N in proper rotations. Remember, that's an S operation. Remember, all these get named. Okay, then you get the special point groups. Special groups. The special groups are special because some of the things I'm going to show you are trickier with them than some of these others. Well, like the things in the example I'm going to show you. This would include D infinity H. This one's pretty important. C N has C in axis, but N is infinite. And an example is H2. So you can imagine, well, here, just so your mind is correct. And so HH. So the infinite number of C2 axes. Yeah, right. So, sorry, I'm a little confused there. Infinite number of C2 axes because here's an axis. There's an axis coming this way, an axis this way. You see, I can keep drawing axes all around the molecule, and since, points technically have no space, I can draw an infinite number of C2 axes. Obviously, H2 is pretty important. C infinity V is the same idea. Same, except you have take HCl. So it's basically the same idea, it's just that it's not two different things. You're missing the mirror plane technically, right? Because D's have mirror planes and C's don't. So I'm not even going to write that down because it's kind of obvious. TD is tetrahedral, meaning that methane's in a group by itself. And then you've got OH, which is octahedral. Okay, so when you take inorganic, if you haven't already, you're going to run into a gazillion octahedral different molecules, and that's where you're going to use a lot of crystal field theory. And in crystal field theory, you may also run into KD, I think, KH. And that's an atom. So that's perfection. That's a perfect symmetry. So argon, xenon, right? So there are things that exist as single atoms. All right, so anyway, so those are the point groups. I think there's a few more, but I'm just not even going to bother. They're rare, like C60. And now I see why there's so many radicals here. What else we got? Oh, we got an eraser. All right, so now let me show you what this is actually useful for. I mean, it's nice to classify molecules and all, but you can do a lot more with this. But I have to show you another way to mathematically do we're going to go back to looking at those symmetry operations, and I'm going to actually give them a mathematical form, a form of matrices that are going to act on vectors. And then it's kind of like, well, that's neat, but so what? You'll see why at the very end. So let me do the E, let's do an E representation as a matrix. And you're guessing correctly, it's an identity matrix. Okay, so again, remember E is do nothing. And you'll see why it's important in a minute. Now, when I operate on Cartesian coordinates, and if you're like me, you have to learn how to do matrix math every now and then. Here, 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 X, here, 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 Y, and Z. Okay, so did nothing. Okay, but I think you just see the idea across. Let's do an inversion. I'm sorry, I'm not going to use the right spot. Inversion, where everything gets, if you recall, I kept saying this last time, that inversions just get all the X's and Y's and Z's and puts minus sign in front of them. And this is kind of childish, you shouldn't even write this down. It's obvious that this turns into minus X minus Y minus Z. Okay, so that one's kind of neat. Let's do sigma H. Okay, a horizontal transformation. And if you think about that, if I like to say that this plane, this XY plane, if this is the horizontal plane, it's going to take something on bottom and put it on top. So it turns Z around. And when those speakers are not that good at this, make sure they're right. Okay, if I'm just simply going to translocate Z across the plane, then it's this. And of course, X, Y, Z. You need to write this down because it's just that simple. X, Y, minus Z. Okay, now trust me, these are going to get a lot more complex. Well, let me make them complex right now. Let's start doing rotations. Now, the thing about a rotation is it can always be held in a plane. So let's go to the X and Y plane. And we're going to move something by a certain angle. So again, when something is rotating, even if it's doing it some weird way, I can always change my axes, my X, Y, and Z axes. I can reorient things, which is perfectly fine. I mean, gravity exists, but molecules really don't feel gravity. It's too weak a force. So I can always turn this rotation into a plane, and I'll turn it into the XY plane. So you remember, I hope you remember, that in trigonometry you learn how to do this stuff. and that is, so I start with x1, I have a certain x1, certain y1 and a certain x1, and then that's going to turn into a different x and y, so an x2 and a y2. Excuse me, so the new x, which I'll call x2, is going to be x1, sorry, what am I doing, x1, cosine of the angle, and then y1, sine of that angle. There you go, there's your new x2, and your new y2 is the x minus x1 sine of the angle. And again, you learned this a long time ago, y1 cosine of that angle. Okay, so, and again, I kept this in the z plane, so z didn't change. That means that rotation is then this. So let me just get a little bit more interesting. Cosine theta, sine theta, 0, minus sine theta, cosine theta, 0, 0, 0, what do you think, 0 or 1? 0 or 1?
1.
1, right. So let's have it act on x, y, z. And you can see I get x2, where am I at? Yeah, I get x1 cos theta, sorry, just x cos theta, plus y sine theta. Okay, the next one minus sine, minus x sine theta plus y cos theta, and then z returns, z stays z. Okay, so that was rotation. Okay, example, let's do the C2. In which case, the angle is 180 degrees, or something like 10%. 80 degrees, but we should never really think in degrees. That's an unfortunate thing that somebody came up with a long time ago. Remember, you got to think in radians, and that's pi. Okay, so if I feed this pi, then the angle is this, and then so what I end up with is minus 1, minus 1, 1. Okay. So let's have that act on x, y, z. And again, the z is not meant to be harmed. If I turn things completely around from here to here, I see that I had a positive x and y, then I have a negative x. And then z never changed because z is in the plane. Okay, so there you go. There's a C2 rotation. Now, what we talked about last time was doing algebra. Sorry, not algebra. Doing operation after operation for reasons you'll see in a moment. Again, the neat thing I can tell you about when my grad students worked on for a long time. So you can do these matrices and do an operation after an operation and see what happens. So let me do a sigma h, then a C2. And let's see what we get. Okay, so this would be, okay, so the sigma h, I have to write the sigma h matrix first. 1, 1, minus 1, right? That, I almost forgot there that turns the z's around. Okay, when I'm operating on an x, y, z, I have to do this one first, and that means that C2 actually comes second. And that is minus 1, 1, 0, 0, 0, 0, 0. Okay. And then again, minus 1, that's minus 1. The next element is going to be, actually I forgot how you do the next element. Oh, it's this one, then that one, and it's actually all zeros. And then the next guy is going to be 0 minus 0, and then the last one, last column, 0, 0, minus 1. And that is an inversion. So there you go. And by the way, if you do C2 followed by sigma h, which is actually an S, it means that molecule belongs in an S2 group in improper rotation. Right? Remember, improper rotation is these two guys. S2 is an inversion. So it's right, it comes out exactly correct. So anyway, so why is that important? Because what we want to do, there's this really neat thing about matrices, is that in the mathematical language, they can be rotated. Okay, that's nice. What does it really mean? It means I can scramble these matrices and have them still be exactly the same. They won't have the same numbers in the same place. That wouldn't be doing anything. They can be made legitimately different and still be exactly the same. And that's really bizarre, but it's actually true. In other words, I can scramble these up. I can make them look different, but they would behave identically, oddly enough. And that is called a block. That means what you do is it's called a similarity transform. Just forget about it. Whatever. Anyway, there's methods to turn these matrices into the same matrix, but not the same. And what you want to do is to make block form matrix. And that's when you turn, you turn this matrix that has a bunch of stuff, and there's a mathematical procedure to do this, and it's really kind of difficult, all right? So we'd like to have computers do that. And what you can do is turn it such that there's only blah. There's only little blahs in blocks. Like this. So I got a 1, a 2 by 2, and a 3 by 3 block. And what I can find is that I can keep doing, however I did, zeros everywhere else. What I can find is that this procedure I did to get this crazy blah to this blah, and then of course they have the same n by n shape. I'm not doing that so well right now. I can do this again and keep trying to get the boxes smaller and smaller until I can't get them any smaller. I mean, it's not unlimited. Obviously, you can't scramble this anyway, how to do the same thing. That's obviously absurd. But you can, again, do this over and over again to get it to the smallest compact form. And you may have heard of this before. It's called an irreproducible representation. Irreducible, sorry. Irreducible representation. Okay, now if you go further in chemistry, you will, no matter what branch I promise you, synthetic, organic, physical, theoretical, you will run into irreducible representations. They're terribly important for just about everything that you can think of. Let me give you an example of a C5. A C5 rotation. Here, let me work here. Okay, a C5 rotation, which makes sense that I work on cyclopentane. 2, 3, 4, 5. Okay, one C5, so C5, obviously does the exact obvious thing. 1, 2, 3, 4, 5. Okay, what does that look like in matrix form? Okay, so I have to have 5 elements for obvious reasons. 0, 1, 1, 2. 5, 0, 0, 1, 0, 0. 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, and 1, 0, 0, 0, 0. Okay, so that is a C5 rotation. And let's have it work on points 1, 2, 3, 4, 5. And again, I remember how to multiply matrices. And this first element is 0 plus 1 times 2 plus 0. So 2, 3, 4, 5, 1. Okay, you see how I do this? I'm representing it like that. So hopefully you see that kind of makes sense. Now here's a crazy thing. I look at this and I can't imagine how this could take another shape. It's obvious how it did what it did. It's painfully obvious how it works. How can it be made to be any different? It can't. Now, this unfortunately does get complicated. And how you do it even, I know just a little bit about how it's done, but not enough to actually do it, because it really involves some very deep mathematics to turn these matrices into other matrices, but still have them be identical. They still do the exact same thing. And how that looks is like this. Here's the actual C5 in the irreducible form. 1, 0. Okay, you may notice I'm giving myself lots of space. Cos 2 pi over 3 sine 2 pi over 3. Sorry, my writing is great. 0, 0. 0 minus sine 2 pi over 3 cos, sorry, over 5, my bad, 3 doesn't make sense. I just can't read my own notes. Sorry about that, doesn't really matter. Well, except I'm telling you something wrong. Great. No award for me. Okay, 0, 0, and then last but not least, 0, 0, 0, cosine 4 pi over 5, sine 4 pi over 5, and I've got one more, and this is minus sine 4 pi over 5, cos 4 pi over 5. Now I can draw my brackets to make it a legitimate matrix. Okay, and here's the block diagonal form, which is kind of obvious. There you go. And I promise you, I'm not going to be remotely going to try to do the example I showed above. I think it would blow my head off. But this is the exact same matrix that behaves the exact same way as this much more obvious one. So, now why is that important? Because it can be used to make what's called a character table. So all the point groups have associated character tables. And I know this is going to be a little hard to digest, but let's do our best. So character. Okay, so a character table is when you take a operation, a symmetry operation, and you put it in its irreproducible form, and it has a certain number of blocks. Each block is characterized by its trace, which is the sum of the diagonal. So the character of the character table is the sum of diagonals of the irreducible representation. On my way. Irreducible rep. Again, that's a symmetry element that belongs to a particular point group. Again, the point groups are made up because the molecule has 3 or 4 or 5 or 6, whatever, symmetry operations that apply to it. Okay, so example E in 3 dimensions. The character is obviously 3. There you go. And that actually has everything to do with the fact that it's 3-dimensional, right? Meaning that it's 3 by 3. Remember, block there'll be an even number, 1 by 1, 2 by 2, 3 by 3. It doesn't have an option about that. It has to be that way. Okay, so let me show you a character table for C2B. This pen is driving me crazy. Let me get a new pen, and then I'm going to show you what it's useful for. I talked a little too much at the beginning. Okay, so character table, then we're going to start reading off the character table, and then we're going to apply it to an actual problem. C2B. And it has these symmetry elements. I'm actually just going to write a few of them. There's actually several more, but for time's sake, let me just do these. Okay, again, I look at each symmetry operation, and I'm going to put it in this irreproducible block form, and it turns out that each one produces 3 blocks. kind of like the examples I just showed. It produced 3 blocks in this case. It didn't have to. And the sum of the diagonals, the trace of each block, in B's case was 1. There was another block that produced a trace of 1, and another block that produced a trace of 2. C3, again, came in the form of 3 blocks. The sum of diagonals was 1. The middle box, the sum of diagonals was 1. The last one was -1. And this guy was 1, -1, and 0. Okay, so what? Well, this is actually shockingly useful. Now, it turns out that, as I just showed you with E will be the dimensions of the number of elements in the block. So the E, an E of 1, the trace of 1, E with the character of 1 has to be just this, not much of a matrix. So if that's the case, we're going to call this, we give this, see I need to put something here, we call that the letter A. Now E, if the trace of E is 2, it had to be this. Right, this is 2-dimensional, so we call it E. And that other one is also A, so we just give them different labels to distinguish them. So anyway, all right, so now what's important about this, because we're really running out of time, if I can use my example. Okay, this is actually the most shockingly important thing you can find out about it. Whatever C2D molecule like water, what I've learned is that these symmetry elements are the symmetry elements of the Schrodinger equation itself. So if you solve the Schrodinger equation for water, because water is C2D, the wave functions have these symmetries. They have to. If they don't, you've done the calculations wrong. Now what I've learned about this is also this 1-dimensional versus 2-dimensional. That means that I will have wave functions that are non-degenerate, but I can't have degeneracies. Right? Remember, I said that only C1 and CS have no degeneracies possible. There's no E's in there. And that's really important, because remember, I told you degeneracies really freaking matter. Also, when it comes to vibrations, these shapes, these letters, again, mean something. So I have 2 vibrations that have the same absorption. So I might not understand that if I don't know to look for it. This thing told me to look for it. These guys are fully symmetric. So that's this. So a molecule like water has to have fully symmetric vibrations. There's one, the other, just like that. I know it had to have 2 of them. It has to exist. So this just told me, without doing actually any math whatsoever, well, okay, that whole matrix diagonalization thing, okay, that was hard, but anyway, we'll get the computer to do it. But without that, I just learned a tremendous number of things that otherwise require extremely complicated quantum mechanics. And instead of doing all those quantum mechanics, I just had to look at the character table and know a lot about its ability to have degeneracies and symmetries and all that jazz. Now, I published an actual example, and that comes from multiplication. So let me show you something you're going to get in 346. And let me show you about a problem that I had in my lab. And that is pyrite, which is D2H, I believe. Pyrite is D2H. Here's pyrite. Highly cycloaromatic hydrocarbons. Okay, actually not that toxic. I know I looked at this and thought that's immediate cancer. And so I can see that I can turn it this way. I see the horizontal plane. And so D2H. Okay, here's the thing that we were seeing in my lab. We had a singlet ground state. Almost everything has singlet ground states. And then when we shine light on it, we go to a singlet excited state. You're going to be getting a lot of this in Keachem lab. Okay, so this is a singlet. Now, lower in energy is a triplet. I'll designate it that way. Okay, now the problem with this is that singlets can't turn into triplets, but we were seeing it happen quite a bit. And that's very strange. Well, since they're different states, they can't really turn into one another. In this case, there's a spin flip selection. Well, you may remember that from freshman. You actually heard something about that. These electrons can't simply flip unless there's something there, an energetic crosstalk. If there's a way to get them to energetically talk to each other, what happens is that your initial state becomes 99% of itself plus 1% of the other guy. So this is due to a perturbation. Sorry, I'm going too fast. And in the triplet state, then becomes 99% of its former self plus 1% of the other guy. Again, to this energy perturbation. The way to do the calculation, and this actually happened, the energy perturbation is a magnetic field. So we were seeing this guy turn to this guy way too much because it was a magnetic field. Now the way to know whether that's true, whether this is happening, is to do this calculation. That's the calculation, the quantum mechanical calculation that tells me whether these two things are melting into each other. Okay, these are cross products. Remember, magnetic fields perturb electrons by the right-hand rule, and that's energy. So again, this guy in its excited state has its electrons warped by the magnetic field such that it picked up some triplet character and the triplet picked up some singlet character. Now, once you've done that, then they can transform into another. They can, and this calculation proves it. D cross D, right? I don't want to do this. I don't think I really know how to do this, to be perfectly blunt. But I just want to know whether it's zero or not. In other words, is this an even or odd function? So it turns out that I can multiply symmetries. I can multiply symmetries and see whether it's even, which means it has a character. So the symmetries multiplied, you see me multiply symmetries. Symmetries multiplied, if that product is symmetric, then this is not zero. And I've proven my point without doing the fucking calculation. That's incredibly useful. Remember I told you that zeros come up a lot in quantum mechanics. And so it turns out that this symmetry is B1. This symmetry, right, so this magnetic field, it's a field, it has a symmetry. It's actually like a rotational symmetry because of the cross product. It had B2 symmetry. And this guy, again, this is a different label. This is it's like A, except that it's odd. So the A symmetry of water was this. The B symmetry is this when it comes to vibration. So they're similar, but not quite the same. And then this guy is B3, I think. B3. Now you've seen me multiply symmetries already. So with every character table of D2H, so I've got one of these for D2H, there's a multiplication table as well. So they always come in pairs. And the way it looks is, what I have to do is multiply these two together, and I look at the table. D1. Oh no, we're out of time. Let me just tell you what happens. These two multiply by each other, turn to B1. Then I multiply these two together, and I got A. A, again, is fully symmetric. That means the integral will not, the left half of the integral does not wipe out the right half. So when I do this integral, I'm going to get a number, which is all I wanted to prove anyway. I don't really care what the number is, as long as it's not zero, and we prove it. Okay? This is very hard. All right. Sorry, I'll get camera.
Turn this off. You have to turn this off.